Okay, so the standard free energy change, or delta G naught, gives us the direction the reaction is going to run under standard conditions. And by direction, we really mean if it's a negative sign here, then it's spontaneous in the direction as written. And if it's positive, it means that it's going to be spontaneous in the opposite direction, right? Because if you just flip the reaction around, then the sign of the delta G also changes because it's simply the products minus the reactants. So that's what I mean by direction here. But we talked earlier that the standard temperature pressure conditions just are simply a chosen set of conditions that allow us to compare all reactions against each other. But we know that in reality, we're not really doing things at 25 C, 1 atmosphere, and 1 molar of all things. In reality, all of those variables are quite different. And so when we drop this degree symbol, then we consider this delta G under non-standard conditions, which just means we can allow those original constraints to float. So this can be under non-pure substances, non-1 molar conditions, elevated temperatures, colder temperatures, etc. So how does this value relate to the standard? Well, it really is just whatever the free energy change is under standard conditions, but then modulated by this extra term. And the extra term is nothing fancy. It just allows us to operate at a different temperature than what delta G was calculated at, which was 25 C, and under different concentrations. So this Q is the same reaction quotient that we talked about in the equilibrium chapters, where it's really just the products over the reactants, but now these are under non-standard conditions. And that should make some sense mathematically, because if delta G is when everything is under standard temperature pressure conditions, which includes solutions where everything would be then at 1 molar, then what would happen if we replaced all of these with 1 molar? Well, this whole term would be 1. Natural log of 1 is 0, so the whole term comes to 0, and so delta G is equal to delta G naught. That makes some sense. So really, the Q here is allowing perturbations from non-1 molar conditions, but if everything's at 1 molar, then these two quantities are equivalent. And I should say, not just 1 molar, but in cases where we're dealing with pressures and partial pressures, then we would be putting partial pressures here that are not 1 atmosphere. So let's just do a quick example where we want to find the overall free energy change, delta G, for this reaction. So this is the reaction we deal with a lot. Nitrogen and hydrogen combine to make 2 parts of ammonia. And we already have a tabulated value for the standard free energy change, which is negative. So we would say that under standard temperature pressure conditions, where all of these gases are at 1 atmosphere at partial pressure, this thing is spontaneous and at 25 C, but we're still at 25 C here. So what happens when we deviate from non-standard conditions? So nitrogen's still at 1 atmosphere, but hydrogen now we have more, we have 3 times more, and ammonia we have a lot less. So how can we tabulate delta G and ask ourselves, what direction is this system going to move, and is it spontaneous from left to right with the conditions we have in the vessel right now? So first thing, we just need to compute whatever that reaction quotient is, which is going to modulate our overall delta G. And since we're dealing with gases here, instead of concentrations, we're using partial pressures, which is really the same thing as gas concentration. So everything else is the same. We'll have the reactant raised to its coefficient 2 here over partial pressure nitrogen times hydrogen raised to the 3rd. So we'll plug in our... Okay, so we can take that value, which we compute, 1.5 times 10 to the minus 5, and plug that in for our expression for delta G, which remember is just going to be equal to the standard delta G, except we're going to change the value Q because we're no longer at 1 atmosphere for all these values. So pop in our tabulated delta G here, which is minus 33 kilojoules, plus the gas constant R. Make sure you're using the correct units here. All your units should go away nicely, so be careful about that. And in this case, times 298K, natural log of our Q that we just computed. So that gives us a value of minus 60.5 kilojoules per mole for the non-standard delta G, which is the actual delta G of the system, and we can compare that to the standard delta G, which is minus 33. So what that's really telling us is that under these conditions, there's actually an even greater driving force for the system to move from left to right, meaning the products are higher higher in energy relative to the reactants than when everything is at 1 molar conditions. But what happens when delta G is 0? So when delta G is equal to 0, let's say delta G equal 0, then as we discussed before, this means that the system is at equilibrium. Because if we were to look at a reaction progress diagram where we have G on the axis here, that would mean that the energy difference between the reactants and the products is identical, which means that there's no driving force for net change from reactant to product or product to reactant. We know that these things are interconverting at the same exact rates because that's what the definition of equilibrium means, but there's actually no net change because the system has no net change to move from this position. It's at the lowest energy conformation of the system. Another implication is if delta G is 0, not delta G naught, but delta G 0, what does that mean for our expression up here? Well, it means that this whole system is 0, which means that we could say like delta G is equal to minus RT ln Q, because I'm just rearranging this expression once the system was equal to 0, which means that if we knew what the tabulated form of the standard conditions for delta G were, and we knew T, then we can actually figure out what the equilibrium concentrations of the system were. Because remember, to get to this expression, we had to say that delta G was 0. That only occurs in this circumstance where the system's at equilibrium. So this is sort of a shortcut to then figure out, well, what are the equilibrium concentrations or ratio of the products to reactants when the system actually has no net driving force. So that's its happy place, which, as we discussed before, is related to then K, because we know K is also equal to the products divided by the reactants. So that's how these things are interrelated here. Action. Another really useful way then to think about this is using a plot like this, graphically understanding what's happening to delta G as the system proceeds toward or away from equilibrium. And so delta G is representing the overall free energy change, not just the standard, which is not that useful, except that it's sort of just a benchmark. And so if we're thinking about here the total free energy of reactants and products, so that's that delta G, or the G that changes the delta G, and this is the reaction progress, we could say that if we're starting up here with just pure reactants, then the free energy change, the delta G, is less than 0, so the whole thing starts to move in this direction. So this is spontaneous because reactants are high on our energy, products are down here at lower energy, so the system is going to move. But if we look at this expression up here, we know that Q is changing in real time, because if we move down this curve, that means we're producing more product and we're destroying more reactants. So the ratio of products to reactants, which is Q, is changing. So that means delta G is changing. So it's important to know that delta G is not fixed, right? Otherwise this would be a straight line. But instead it's this curved line, which means delta G gets smaller as we start to approach equilibrium, which should make sense, because at equilibrium then the change in free energy is 0, and that's when we have the equilibrium mixture of stuff in the system. which is then defined by this expression, because that's when delta G is 0, and now the reaction mixture is going to have concentrations of products and reactants that are equal to that equilibrium constant K. And that means that if we wanted the system to proceed further towards pure products over here, that's no longer spontaneous, because that would be a positive delta G, where the product energy, free energy, is higher than the system is down here. So we would have to put energy into the system. But we could also start with pure products in the system as a separate example, which is sort of denoted here. Beginning with pure products, free energy also decreases, right? And it's going to decrease back to the same equilibrium position where delta G is, with the exact same equilibrium mixture. And so we sort of touched on this when we talked about equilibrium a couple chapters ago, but it's important to understand from an energetic perspective what that really means. It means equilibrium is equilibrium. That's defined by K, which is a constant. It's just a constant ratio of products to reactants. But the driving force to get there is the overall free energy change between products and reactants, and it doesn't matter which direction. If it's positive or negative, depending on what you have in the system, it's always going to strive towards zero, which is the lowest energy point of this system. And that's what the universe is going to prefer.